Okay, physics studies, this is another little question about Bohr's energy models and absorption and spectral lines in gases. So this is question 7 on page 294. We've already talked in class about the energy levels of elements, and hopefully that's starting to make a bit of sense. I'm hoping that by going through this question it will become a little bit more clearer, but also you'll be able to use the values effectively and get some solutions yourself when you're looking at the practice questions. So anyway, here we go. This is should be a familiar kind of view of what we're talking about. This is a Bohr's energy level diagram, right? So this question is specifically talking about mercury, and it's got some of the possible energy levels that can happen within the atom itself. In other words, some of the possible energy levels that the electrons can operate at. We have to remember that this is based on a quantized model, so the electron can only exist at these energy states. It cannot exist in between. So this is where the quantum explanations start to make a little bit more sense. So question 1, it says, it talks about mercury being used in fluorescent tubes, and it's saying that an electron in mercury has dropped from energy level E to energy level B. So the energy's been, the electron's been excited, and of course if this was a standard fluorescent tube light, it would be excited by electrons. So an electron would come in and excite another electron, which would then jump up. In other words, electricity. An electrical current would energize this electron, and it would be jumped up to various different energy levels. So in this case it's already at level E, and it's going to drop down to level B. So it's going to end up here. So the question is, determine the energy of the photon emitted. So this is question A. We need to know the energy of the photon. Well, we're going to look at the change in energy, right? Because that change in energy from here to here is going to be equal to the energy of the electron. So it's pretty straightforward. We're looking at the difference between this energy and this energy here. So I would just literally subtract them away from each other. I've got an initial energy of negative 2.68 electron volts, and I'm going to just subtract the new electron volt value from that. So I've got my initial energy minus my final energy, so 5.74. And that gives me a change in energy of 3.06 electron volts. Okay, so that's it. That's going to be the energy of the photon. If we want to visualize what that looks like, hopefully it's clear. Once this drops down, there's your photon. That's your photon coming off of here, and it will be equivalent to the energy drop, which is what we just calculated. Okay, pretty straightforward. Question B. It asks, what is the frequency of the photon that would be emitted? What is the frequency of this photon that would be emitted? So I'm trying to find the frequency. Well, what do I know? Well, we've already taken a look at Planck's constants, and we know that, hopefully you can remember that the energy of a photon is equal to Planck's constant times the frequency. So honestly, right now we're just going to rearrange this and solve for the frequency. Pretty straightforward. So if we do that, we plug it away, we're going to get 7.39 times 10 to the 14 hertz. Okay, pretty straightforward. No major problems so far. Lots of just plugs and chugs. Question C, let's put that over here. Let's put a box around that. Put a box around that. Let's do question C. Question C says, what is the wavelength? Well, now we're getting pretty straightforward as well, aren't we? Because wavelength is, as we know, we can use our universal wave equation. The speed or the velocity of a wave is equal to lambda times the frequency, and we just worked out the frequency, and the speed of light is constant, so lambda, which which is the wavelength, is the speed of light divided by the frequency. Easy. Okay, that gives us, what does it give us? It gives us 406 nanometers. Already I'm looking at that number and going, yeah, that makes sense, because I should know, as a memory, I should know that the electromagnetic spectrum, the visible light, goes from 400 to 700. So this is on the smaller wavelength scale, so this is going to be violet, this is going to be a blue light. And oh, lo and behold, what have I done? I've just accidentally solved the last question. Because question D says, what is the region of electromagnetic spectrum that you'll be producing? Well, again, from memory, and you do need to memorize it, you should know that the spectrum goes from 400 to 700. This is at the higher energy level, really right down there. So this would be violet, that high energy light. Okay, I think actually we're going to go one step further. Those are pretty straightforward. I think we're going to go and take a look at question 8 as well, which is a follow-up question. It's asking, let's see, yeah, it's saying determine the quantity of energy that would be required to ionize a mercury atom if its electron is already excited to level E. Okay, so just a bit of terminology here. So this is actually asking from this question at the beginning, if it's already at level E, what's the energy required for ionization? Oops, I always get my S's and Z's mixed up here. That's a product of being confused with two different language systems. I think I'm going to go with Z, whatever, you can figure it out. I never know those, but Z's or S's in organize, you know, it's being English, that's the problem. Anyway, ionization. Ionization is when the electron is essentially lost, it's gone. It's at this sort of hypothetical zero energy level at the top. It's going to be lost and it's gone from the atom. This is what happens in plasma. Okay, the fourth state of matter. You lose those electrons; they get kind of flung off because they have so much energy, and it changes the structure of the gas. It changes the behavior of the gas. So we'll leave it there for now. But for our purpose, it's just at the zero energy level. We can still count it as an energy level, but it's just important to know that it's going to be basically gone. So we're asked the question, what is the energy needed to get it to that level? Well, ionization, if we have our energy levels going this way, because remember, of course, sometimes you'll see them flipped, sometimes you'll see them with 0 at the bottom and then a positive at the top. But in this case, we want to get to our 0, that's our ionization, and then we're just going to subtract the energy that we were at. So this question is saying we're already at E, so I'm going to subtract my negative 2.68 electron volts, and well, you can see, pretty obvious, it is 2.68 electron volts. That's going to be my answer. I need that amount of energy to get myself to 0 to ionize. Simple as that. Anyway, do some more of these practice questions, and we will move on a little bit more in class. Over the next couple of days, we'll be looking at de Broglie's wavelengths. We have a little bit of a lab on this stuff, so you'll get to see it. In the lab, you'll get to take pictures of it, document the absorption and the emission spectrum lines, and it's all fun stuff. Anyway, thanks for watching. See you soon.